everyone. Good morning, good afternoon, good evening. Oh, we are around the world. I'm Ray from AMD and Linux graphics team. I live in Shanghai right now, and it's a long time to see you since last XDC. And I'm very happy to see you again here, even with the online conference. At this moment, it's my great honor to have the opportunity to talk about the Linux software solution for the secret buffer object to all of you in the conference. And we designed the solution early this year. In Linux, we have some specific use cases that is required secret buffer support. Okay, let's move to the agenda. Here is the agenda of this talk. I will introduce the background, trusted memory zone, and the supported platforms such as APU and discrete GPU. And we will introduce the secret buffer object and how does the kernel and the Mesa buffer do the handshake, secret policy, secret read and write operations. Above items are the dependencies and the conditions for the secret buffer solution. And after that, we will go to the implementation part, which has the IB protection mechanism and the secret command submissions on graphics, SDMA, and vSyn. And then discuss the display secret from buffer. After that, we want to show you the unit test for secret buffer from the libdm part and the related parameters on the kernel and Mesa, and the data comparison sample between the encryption and un-encryption content. And finally, we will talk about the future working with the open source secret solution. Okay, let's go to the background. Firstly, memory encryption is a very popular topic recently. Most people would like to make sure their personal data cannot be accessed by any other guys, So we raised the memory encryption feature that protects the content cannot be accessed by unauthorized applications. So on Linux, we provided the secret buffers solution, which used the memory encryption for the content protection in our GPU platforms. We developed trusted memory zone to support video memory and system memory encryptions. Then Linux kernel and Mesa OpenGL and the user space applications are able to leverage the functionality of trusted memory zone to implement the secret buffer object for the protection on many user scenarios. Okay, move to the trusted memory zone. And what is the trusted memory zone? The trusted memory zone, we call it the TMZ, as well, is a method to protect the contents being written and read from memory. This memory presents both the system memory and the video memories. The new GPU support the full bandwidth ICE cipher. That's actually the hardware protection, which is much safer. So all the trusted write and trusted read should go through the S cipher before hitting the memory. And it's able to keep the raw memory data in safe under the cipher and cannot be accessed by the regular read and regular write. We use the TMZ bit in our GPU VM table and the trusted transactions state to provide multiple protection. Even if the TMZ bit is configured. The content is still in safe and not exposure. So it's very safe at that time. And let's move to the hardware platform support. AMD has two kinds of GPU platforms that are the integrated GPU and the discrete GPU. And we also call integrated GPU is in the APU platforms, like CPU and plus GPU. Right now, let's look at the difference for these solutions. In discrete GPU, only video memory is able to be encrypted. That's because the discrete GPU engine is unable to encrypt the system memory on unknown CPU platforms. So the trusted memory zone can only set up the video memory on discrete GPU platforms. However, in integrated GPU platforms, it's actually the APU platform. In this kind of platforms, both the video memory and system memory are all able to be encrypted. Okay, let's go to the definition of the secret buffer object. AMD GPU supports 64-bit page table entry, and there are the page-based address, fragment, and the properties fields such as read, write, execute, and whether it is in system memory, and the cacheable and valid bit. We use one of them, bit3, as the secret property. Why the bit is set in page table entry? The page that is pointed by this entry will be put into the trusted memory zone, and this can be encrypted. According this definition, AMD GPU kernel implements a buffer object-based protection. That is because the buffer object is the basic management unit in the Linux direct rendering infrastructure. All the memory operation is based on the buffer object, so we use the secret buffer as the unit as well. And all the TMZ bits should be set in the page table entries. If they are in the secret buffer, no matter what is system memory or video memory. Okay, let's move to the kernel. Kernel and Mesa, secret buffer definitions, and the Handshake. And there are three user mode API that we introduced with this feature. The first one is the gem create encrypted. A kernel driver provides this flag in the gem create IO control. That's the BO level protection. And I mentioned before, and then libdm Mesa will use this flag for the secret buffer allocation. Mesa use allocate buffer to decide whether this buffer is secret or not, because the user mode is aware which data they should be protected. If the gem create encryption flag is set by Mesa, and all the TMZ bits of the whole page table entries for this buffer must be set as well. And the second one is the IB flag secret. This flag is indicate to the indirect buffer is trusted or not, and Mesa uses this flag in IB handle of the command submission context to inform the kernel and whether the graphics engine needs to translate to the trusted state. And the third one is ID flags TMZ. That is very simple, and that's to indicate the TMZ capabilities is integrated or not on current platforms. and Mesa use this information flag to be aware of whether the current GPU support TMZ or not. Okay, let's move to the security policy. We have two kinds of blocks to need introduced. One is untrusted block. CPU as the untrusted block that is unable to decrypt the secret buffer with the trusted memory zone. User cannot get raw data from CPU address, even the address is k-mapped with CPU page tables. And the other is the trusted hardware block. Owning the trusted hardware block has the capability to describe the secret buffer. All the encrypted memory is only able to decrypt the GPU page table mapping. We have any trusted hardware blocks such as the graphics, SDMA, VCN, and JPEG display engine. Let's move to the write operation modulation table. I describe the secret write operation capabilities. The first column. The first column indicate the trusted transaction trusted state, and the second is actually the TMZ bit in the GPU table, and the third is modulation result that marks the trusted hardware block, whether it is trusted or not, and the last column is the encryption state in TMZ. And from this table we can know only one of the TMZ bit in GPU page table and the transaction trusted state is on, and the data should be protected under the trusted memory zone, and that means if somebody mistaken to misconfigure the TMZ bit in the GPU table, the content in the buffer is still in the protected mode, so that's very safe. Okay, let's move to the read operation modulation table. It describes this format of the read operation table actually is similar with the write table. From table, we can only the modulation data its own, and the TMZ bit is set in the GPU table at the same time. Name the results can be decrypted, and the decrypted state in TMZ will be on. That means we have to apply all the trusted mode and the secret bit in the system, and then we will get the decrypt data on the protection mode. So, okay, let's go to the next page. For now, let's talk about the per IB protection mechanism. What is the IB? Let's say the indirect buffer. If you joined XDC last year, you may know the indirect for buffer detailed, and if you want to know more information, you can listen to the recording of Let's Talk in the YouTube. Okay, here the buffer, the IB is command buffer which stores the package, which the graphics queue is used. The kernel implements per IB protection to execute the command submission. And please look at this diagram. This is the graphics command ring, and we actually leverage the producer and consumer pattern to present the data structure. We have the GraphQL is consumer and the kernel is a producer. Once kernel produced a package writing to the command buffer, the write point will be increased 1, and we once the graphics queue consume a package from the command ring, and the read point will increase 1 as well, and they run in the same direction in this command ring. The IB is another indirect command buffer which embedded in the command ring, and the many operations package are actually in the IB. So firstly, let's look at the blue one, which is the legacy case. Once IB emitted, the kernel will inform the hardware into the non-trusted state. That means this IB will execute the regular read and write for data buffer in this IB. The data is not encrypted, so CPU is unable to write and read the raw data in this. The data is not encrypted in this buffer, so the CPU is able to read and write the raw data in this buffer. So that is the legacy case. If we let's look at the original one. It is the secret IB. Once this kind of IB emitted, the kernel will enforce hardware block translates to the trusted state. That means the IB will execute the TMZ read and TMZ write for secret data buffer, and this IB, the data will be encrypted and can be decrypted by the trusted hardware. And CPU is unable to read and write the encrypted buffer at that times. This is the operation for the command ring to handle the secret buffer case. Okay, let's move to the command submission with secret buffer on 3 different engines: graphics, SDMA, and VCN. The graphics use the from TMZ bit with the packet frame control package to control the graphics engine into the trusted state. Once the IB finished, the kernel needs to clear the frame TMZ bit to send the engine back to normal. SDMA as another trusted hardware block, which is to use the TMZ flag in the page table to decide to do the regular read and write or trusted read and write. While the kernel used SDMA to do the secret buffer copy, the kernel needs to set the TMZ bit at OP code of copy linear package to let SDMA know it's doing the secret buffer copy. A VCN engine doesn't need the kernel support to switch trusted level during the context switch, because it's able to switch by itself according to the TMZ flag in the page table. That will be smoother while we are doing the video playback on the secret buffer. Okay, let's talk the display engine. Display engine is different than the others. The secret state of display engine is based on the register setting. That means the display buffer only program a bit in the register to switch the secret state instead of using the TMZ bit of the page table. In this case, it allows the secret access to the secret buffer in VRAM without using page tables. As we know, this display buffer may use direct access for the local frame buffer. So at that time, there is no page tables for traditional TMZ flag setting. That's the reason we have to use the rigid setting here. Okay, we initialize the security test suite in libdm and AMD GPU test. This test suite is to verify the security buffer related functionalities in the kernel and with the user mode API from IO control. They are to verify the page tables, flags, graphics, and SDMA command submissions, and security buffer migration. For now, they are still in progress on upstream. And please note, we use the TMZ kernel parameters in AMD GPU kernel module and set AMD debug environment variables as TMZ to enable this feature. Okay, let's look at the data comparison. Firstly, this is the raw data pattern, dead beef, in the buffer. After it's encrypted, the data will be unknown and saved data. So that is reason. So that's very clear. The encryption data, and nobody can know what they are. These are the links for the kernel, libdm, and the Mesa changes for the secret buffer. You can refer the source code here. Finally, let's talk about the future work on this feature. Actually, recently, we would like to support Widewine L1 for AMD GPU platforms. So what is Widewine? Widewine is the digital write measurement technology provider that's used by Chrome and Firefox, this kind of the web browsers. We would like to have the Widewine digital write measurement solution both on the Linux and Android. And the secret buffer with trusted memory zone is the key functionality which is required by Widewine. And both TMZ plus HDCP were leveraged by Widewine to set up a safe channel for the digital million data owner on the AMD platform. We actually are working on the upstream of full end-to-end solutions right now. Okay, thank you. Any questions? And please leave the message and note here, and feel free to send me the email. And for now, I'm very appreciative to the X.Org Foundation to give us an opportunity to present the secret buffer here to all of you. I'm very happy, and thanks X.Org, thanks to the X.Org Foundation very much, and see you next year. Thank you.